Cancel. Oh, stop. All right.
You got to click on slideshow again. Ooh,
It doesn't say we're paused. Resume share.
it says recording to me.
It doesn't say that. So I think we're recording, guys. So we're gonna keep on. Let me move this back down and that back down. And no, I got to get you back to your presentation. Sorry for the interruption. Now we'll try this one last time. Okay. And then display settings one more time. Duplicate. Now back to where we were. Elements.
Excellent. Does that look good now?
Perfect.
Perfect. Okay. So as I was mentioning, each element, if you run electricity through it or you heat it up, it glows with specific colors. So hydrogen glows with specific colors, helium glows with specific colors, sodium, mercury. Every element on the periodic table has a particular set of colors that it glows with. And so when we take the light of an object like the sun, this is a spectrum of our sun. If you just take light from the sun and pass it through a prism and spread it out, you get what we call a continuous spectrum. All the colors of the rainbow, right? Red, orange, yellow, green, blue, indigo, and violet. You'll remember studying Roy G. Biv, the colors of the rainbow. And you'll notice in the sun, there are a couple colors that are missing. There's a particular color of red light that's missing, a particular color of blue-green light that's missing, and two colors of violet-blue light that's missing. And those might sound familiar to you because I said a second ago that those are the exact same colors that glow when I heat up hydrogen or when I run electricity through hydrogen and cause it to glow. And the reason those colors are missing in the sun is there's an outer atmosphere of the sun that's cooler than the rest of the sun, and that atmosphere is absorbing those colors, and that absorption is coming from hydrogen atoms. So we know that our sun contains hydrogen because we see this absorption from hydrogen atoms. How much light gets absorbed tells us how many hydrogen atoms there are. And what we know from studying this is that our sun, like that stars that I showed you a second ago, is about 74% hydrogen, 25% helium, and about 1% everything else, right? So our sun is the same composition as most of the stars out there. And we know that from breaking the light into its component colors. We have devices on telescopes. This is a giant telescope that the University of Virginia is a partner in Eastern Arizona called the Large Binocular Telescope. Each of these mirrors that you see inside the telescope is bigger than this classroom. They're 27 feet across from side to side, 8.4 meters inside. It's actually the largest telescope in the continental United States. And the University of Virginia built a spectrograph for this telescope. It's a device that breaks the light into its component colors and allows us to determine what things are made of. Other telescopes, like the Hubble Space Telescope, have spectrographs on them on board. Mr. Garrison mentioned that I worked on a spectrograph called the Far Ultraviolet Spectroscopic Explorer. It was a NASA satellite launched back in 1999 that did this one thing. It worked in the ultraviolet portion of the spectrum, which means that ultraviolet light doesn't get through our atmosphere. So in order to see it, we have to put our telescope up above the atmosphere, which is why we had to launch it on a satellite. And then spectroscopic means it didn't take pretty pictures of the sky. I don't have any pretty pictures to show you from FUSE. It took ultraviolet light, broke it into its component colors, and we were able to measure things like how much hydrogen, how much oxygen, how much phosphorus, how much calcium, how much nitrogen there were in the gas between the stars. So that's a little bit about how we determine some of the things we're going to talk about today. We also do it, and I also do it with the radio telescopes. There's this giant radio telescope in Green Bank, West Virginia. It's about a 4-hour drive from here in eastern West Virginia. It's the largest fully steerable telescope in the world. And it looks like a giant satellite dish because it doesn't pick up optical light, but actually picks up radio waves. And it turns out molecules like water molecules and carbon monoxide and carbon dioxide and ammonia, all these molecules emit radio waves. And by measuring how much of these radio waves we receive, we can actually measure how much of that molecule there is in space. All right, that's a little bit about what I do, but now I want to talk about the origins of the elements. And in particular, I want to talk about the elements that are important to you and me, right? And so there are some elements that are really important to you and me. And so let's start with this question. What elements are important to you and me? What are you and I made of? So what's a human being made of? What element? Yes.
Carbon.
Carbon, right? So one thing, if you decide to pursue, you're fine. If you decide to pursue medicine, for example, or biochemistry, you're going to take organic chemistry. Organic chemistry is that branch of chemistry that deals with carbon compounds. And because organic chemistry is often said to be the chemistry of life, it's very natural to think that we're mostly made of carbon. But it turns out we're not mostly made of carbon. What are humans? What's a human being? It's a really good guess, but what's a human being mostly made out of? Water. You're mostly made out of water. And what's water mostly made of? Hydrogen, right? Because the chemical formula for water is H2O, right? 2 hydrogen atoms, 1 oxygen atom. But I want you to think about that a little bit differently for a second. And let's think about how much each of those atoms weigh. Because really, when it comes to what you're made of, we're not interested in the number of atoms, but the weight of those atoms. So what is the atomic mass of hydrogen? How much does a hydrogen atom weigh? 1. How much does an oxygen atom weigh? 16. Fantastic. So if you think about it for a second, what is water mostly made of? Oxygen. Because water, the oxygen outweighs the hydrogen by a factor of 8, right? The 2 hydrogen atoms have a total mass of 2 and the oxygen a mass of 16. So you're actually mostly made of water, and water's mostly made of oxygen. So what are you mostly made of? Oxygen. Turns out you are about 65% oxygen. You're about 18% carbon. So carbon was a really good guess. That's what you're made of second most of all. Hydrogen is about 9.5%, and then everything else makes up just about 5% or so. Nitrogen, 3.3, and then a couple percent of everything else. But you're mostly made of oxygen. Let's think about this room for a second. What is this room mostly made of? So if I look around this room, the air in this room doesn't have much mass to it. So the air in this room isn't contributing much. What mostly makes up the mass of this room, I'm going to argue, are these cinder blocks right here in the walls. What are cinder blocks mostly made of? Concrete. All right. So what's concrete mostly made of? Okay, silicon's a great guess. So why silicon?
Sand.
Sand. That's right. So silicon comes from sand. But what is the chemical formula for sand? You remember? It's quartz. It's silicon dioxide. It's SiO2. So what's the atomic mass of a silicon atom? If you don't remember, you can look over. 28, exactly. So it's element number 14. So the atomic mass of silicon is 28. What's the atomic mass of 2 oxygen atoms? 32. So what is silicon dioxide mostly made of? So what is concrete mostly made of? Oxygen. The other thing that somebody didn't mention, and just for those of you that have done it, anyone who's ever made concrete knows that you actually, a big part of the mass of concrete is the water that goes into the concrete. So it's also, the walls are also surprisingly made of a lot of water in that concrete, which, as we already learned, is oxygen. So you're mostly made of oxygen. So the things I'm interested in talking about is, where did the carbon and the oxygen in our bodies come from? Another element that I'm going to spend a minute talking about is gold. Right, because humans are fascinated by gold, and I think most of us are looking around the room are probably carrying a little bit of gold with us, right? So in my case, it's my wedding ring. I see many of you have like an earring, or you might have a watch that has a little bit of gold plating on it. If you're not carrying any gold jewelry with you, if you're carrying one of these, you're carrying a little bit of gold with you, right? Cell phones, gold is an excellent conductor of electricity. It's found, a little tiny bit of gold is found in all modern electronics. So you're carrying a little bit of gold in one of these. You're also, not intentionally, carrying around a little bit of, right next to gold on the periodic table, gold, by the way, is 79. Right next to it on the periodic table, number element 80 is mercury. Right? If you've eaten any fish, or frankly, if you've eaten any food, you've got a little bit of mercury inside of you. So you're carrying a little bit of mercury. There's silver on the periodic table. Where does gold come from, or mercury? But I'm just going to stick to gold because I think it's more fascinating to us. Where does gold come from on the periodic table? How did it get there in the history of the universe? What did it have to go through to get here to be in my wedding ring, for example? So those are the things we're going to talk about: carbon, and hydrogen, carbon, oxygen, and gold. So let's talk a little bit about the periodic table of elements for a second. The periodic table of elements was developed by Dmitry Mendeleev in 1869. And a couple cool things to know about the periodic table of elements is, first of all, when Mendeleev developed it, he actually developed it sideways compared to the way we do it. So we organize everything according to columns, right? You'll remember from chemistry, everything in a column behaves chemically the same. And when you look at the outlay of the periodic table of elements, or just how it's how it's laid out like that, people often look at it and say, why is it laid out in such a crazy format? I mean, why is it laid out like this? I mean, why are these big gaps in the periodic table of elements up here? Why do we have 10 and then finish with 18 over there and then 36? Why is it laid out this way? And Mendeleev was the first one to start figuring this out. And another amazing, and I'll tell you more about Mendeleev's work in a second, but another amazing thing I want to tell you about the periodic table of elements is that the periodic table of elements not only contains all the elements that we know of, it actually contains all the elements that there can be in the universe that things can be made of. If there is anything in the universe that is made of protons, neutrons, and electrons, that's made of regular matter, it is on our periodic table of elements. We are not missing anything from the periodic table of elements that things can be made of. And that is a truly remarkable statement. Students have often told me over the years that if a UFO comes and it lands on the Earth, we'll know that it's a UFO because it'll be made of elements that we don't have here on Earth. And the answer is no, it can't be. If it's made of elements, it's on our periodic table of elements. And the reason I can say that is if you look carefully at the periodic table of elements, you'll notice there's nothing missing. You'll remember that the atomic number is the number of what in the nucleus? Protons. It's the number of protons in the nucleus. So the number of protons, and protons only come in whole protons. You can have 1 proton or 2 protons or 3 protons or 4. You can have, 42, 43, 44 protons, but you can't have 42 and a half, or you can't have 43 and a half. You can only have whole protons. And if you just count the numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, you'll notice there are no missing numbers on the periodic table of elements. Now, that hasn't always been true. When Mendeleev developed the periodic table of elements, you will notice that he started laying it out the same way we do today. You'll notice but again, remember, he's doing it in rows instead of columns like we do it today. But what I want you to notice is that there were places on his periodic table of elements where he had a question mark. What Mendeleev realized is that this layout that he discovered for the periodic table of elements wasn't just a convenient way for humans to organize the elements. It was actually telling us something fundamental about the way an atom is put together. And what he realized is that these holes in the periodic table of elements, these places where it looked like there should be an element, but there was nothing there, meant to him that there was an element there, we just hadn't discovered it yet. And so if you look at Mendeleev's table, you'll notice that around 45, and you'll notice up there around 68 and 70, there are question marks. All of those elements have since been discovered, so that today, when we look at our periodic table of elements, you'll notice there are no elements missing. And the example that I used a second ago, 42, 43, 44, I didn't randomly pick those numbers. Probably the most fascinating one on there is element number 43 on the periodic table, technetium. There is no stable form of technetium. Every form of technetium is radioactive. And the most common form of technetium is so radioactive that half of it decays in a period of just a couple days. Now, in the 1920s, when you looked at a periodic table, about 100 years ago, when you looked at a periodic table, there was a hole. There was no element 43 on the periodic table. We knew there should be an element there, but we'd never seen it in nature. And it wasn't until we developed nuclear technology and the ability to create elements through nuclear means that we were able to create technetium. Now, technetium is actually a very, very useful medical tracer. About 80% of all radioactive tracer tests are done using technetium. We manufacture it in special nuclear reactors, but because it decays in just a couple days, when that material is made, it has to be airshipped to the hospital where it's going to be used, and it has to be used right away. They can't put it on a shelf and store it because it's just decaying so quickly. But in any case, we can make technetium today. And that's true of all the other elements on the periodic table. Now, some of you might be wondering, but wait a second, I've heard that we're constantly making new elements up here on the top end of the periodic table. Element 118 or element 117. Aren't we always making bigger and bigger elements? And the thing to know is that every element that above uranium and above on the periodic table of elements is radioactive, and it's unstable and it decays. But these giant elements that we make today are so radioactive. They're so unstable is probably a better way to put it. They're so unstable that they decay within a matter of seconds. The longest ones last just a few minutes long. And the way we make those elements is we take a giant atom smasher and we take big molecules like radon, for example, and we smash them together. And for a brief second, as we smash them together, they create this one atom of this new element down here. But that one atom is so unstable that within a second or two, or at best a few minutes, it disappears. So you can't actually build anything out of them, right? So element 118, I forget what the new name is. I don't know if your periodic table has it. So ununoctium was the unofficial name. It's been given a new name, but I haven't been keeping up on the names of the big elements down there. But we're never going to make anything out of element 118 because it's so unstable and it lasts less than a second that even if I gave you a whole bunch of it and said, make something out of it, 1 second later, it would all be gone, right? It would all decay away into other things. So nothing in the universe can be made out of these heavy elements because they just don't last. So our periodic table contains everything there is in the universe. All right, since you know the structure of the atom, I'm going to skip over those to save a little bit of time. So the question is, where did all these things come from? How did it all begin? Well, the first thing we're going to talk about is not the atoms themselves, but those component parts that make them up. So you will remember that a hydrogen atom, which has atomic number 1, is made of a single proton. A helium atom, which is element number 2 and an atomic mass of 4, has 2 protons and 2 neutrons. And carbon over there has an atomic mass of 12 because it has 6 protons and 6 neutrons inside it. The first question is, where do those building blocks of matter come from? Where do the protons, the neutrons, and the electrons come from? And the answer to that, to me, is absolutely fascinating. So it turns out that the stuff that you're made of, the protons, the neutrons, and electrons, were actually made in the Big Bang. They were made in the first few seconds of the universe. And I think that's really impressive to me because something that Mr. Garrison and I probably experience is every now and then when I get up in the morning, I'm starting to feel kind of old and a little bit creaky. And I just remember now that as I'm feeling old, just look at my hand for a second and realize the stuff that I'm made of, the protons, the neutrons, and the electrons that are in my hand, my protons are 13.8 billion years old. That's how old they are. That's how old you are. You are made of stuff that's 13.8 billion years old. Now, how do we know that these things were made in the Big Bang? Well, it turns out that we know what the universe is like today, and we know that the universe is expanding. So we can take the laws of physics and run them backwards. If we know what the universe is like when it's expanding, we can imagine what the universe is like as we shrink it smaller and smaller. And as you can imagine, as you shrink the universe smaller and smaller, it gets hotter and hotter and hotter and hotter until in the first few moments after the Big Bang, the universe is incredibly hot and incredibly dense. Now, you might say, well, that's great, but how do we know all that works, right? How do scientists know that you're just not making this up? Or how do you know that you're not mistaken by running the laws of physics backwards? And the answer is because we can recreate the conditions of the Big Bang right here on Earth. And that's what we do in particle accelerators. On the border of France and Switzerland, there's a giant particle accelerator where we smash protons and antiprotons together. And when we smash them together, for a second, as the two of them meet, the temperatures, the pressures, and the densities in there are the same as they were just a tiny fraction of a second after the Big Bang. We can recreate the conditions of the Big Bang here on Earth. It's one of the reasons we build giant particle accelerators like this. And we can test whether our ideas of running the laws of physics, just to imagine what the universe is like as it gets smaller and smaller, we can predict what the conditions were like a tiny fraction of a second after the Big Bang, and then recreate them to see if we were right. And now, after having accelerators like this for over 20 years, we have modified our understanding of the Big Bang so that we understand quite well what was going on in the first few minutes. Excuse me. So we know quite a bit about the first few minutes of the universe. And what we know is that the early universe was so hot that it was filled with a very energetic form of light called gamma rays. You'll remember the electromagnetic spectrum. The most energetic form of light are gamma rays, and they are released by things that are incredibly hot, things that are tens of millions of degrees or hotter. And that's what the early universe was like. And the early universe was filled with these photons of light represented by the yellow squiggly lines down there. And these photons of light had so much energy that every now and then, two of them would collide with one another. And when they would collide with one another, they would make a piece of matter and they would make a piece of antimatter. Now, they do this through Einstein's famous equation E equals mc squared. And for those that haven't heard of this equation before, what that tells us is how much energy it takes to make a piece of matter. If I know the mass of something, I can calculate how much energy it takes to make. It's kind of fascinating someday to sit down and calculate how much energy it took to make you. And you'll be surprised at the phenomenal amount of energy that it goes to make the matter that you're made of. But E equals mc squared tells us how much energy it takes to make a piece of matter. So if these two photons of light collide with one another, they always make a piece of matter, like a proton, and a piece of antimatter, an antiproton. And the only difference between the matter and the antimatter is their electric charge. The proton has a positive charge, the antimatter has a negative charge. What happens the vast majority of time in the early universe is because those two have opposite charges, they're attracted to one another. And as they attract one another, they annihilate, and we get back the photons of light that we began with, which is really uninteresting, right? It goes from light to matter, from matter to light again. And it all happens in a tiny fraction of a second. But every now and then, for reasons that physicists don't yet understand, the universe did not make the corresponding piece of antimatter, or it made the antimatter and the antimatter decayed and disappeared from the universe, so that a tiny fraction of matter was left over. And that is the matter that you and I are made of. That is where our protons and our neutrons came from. They came from energetic light in the early universe. This question of why the universe made protons and not antiprotons, and why it made neutrons and not antineutrons, and why it made electrons and not anti-electrons is a very active area of research in physics today. And I guarantee that the person that discovers the answer to this is going to win the Nobel Prize in physics. But my generation's been working on this question for about 20 years now, maybe a little bit longer. We still don't have an answer. I'm hoping it's somebody in your generation that figures out why it is that the universe made the matter, but not the antimatter. But in any case, that we call it an asymmetry. That asymmetry, that creation of matter, but not antimatter, is what resulted in you and me. But that's what resulted, that's where all of your protons and all of your neutrons and all of your electrons came from. You were made, at least the fundamental building blocks were made in the first few seconds of the universe. All right, so what happens next? Well, now we've got the universe filled with all these protons, neutrons, and electrons. We're going to ignore the electrons for a minute, and the protons and the neutrons start colliding with one another. And a proton and another proton can collide and make a heavy form of hydrogen. That heavy form of hydrogen can combine with another proton to make a light form of helium. Two of those light forms of helium can combine together to make a heavy form of helium. Nuclear reactions begin in the universe. And what these nuclear reactions do is they start building elements on the periodic table of elements. 4 hydrogen atoms combine together to make a helium atom. Helium can combine with things to become lithium. And we start making these elements on the periodic table. There's a couple problems, though. The first problem is that the universe is very rapidly expanding. In fact, it is expanding so rapidly, and as it expands, it cools off, that after about 100 seconds, and this is really amazing, right? The Big Bang happened 13.8 billion years ago, yet I can tell you with a great deal of accuracy what happened in the first 100 seconds of the Big Bang. That's how good cosmology has gotten about the study of the origin of the universe. We know quite well what happened in the first 100 seconds of the universe. And after about 100 seconds, the universe is expanding so fast, it's cooling off, that actually they continue for about 3 minutes. And at 3 minutes, the universe has gotten so cold that the nuclear reactions shut down. So for the first couple minutes of the universe, we've got nuclear reactions building hydrogen into helium, helium into lithium, lithium into beryllium. But the beryllium that's up there is unstable and it very quickly decays. And so it turns out that this is what the periodic table of elements looks like today. And much to Mr. Garrison's disappointment, this is what the periodic table of elements looked like 3 minutes after the Big Bang. There was hydrogen and helium and a tiny bit of lithium. And I only include the lithium here because there was a tiny amount of it made, but the universe was 75% hydrogen, 25% helium. Chemistry class was really boring back then because, right? So helium is a Nobel element and it doesn't form molecules with anything. So you've got hydrogen and helium to work with, right? Chemistry class was really fast back in those days, except that there was no Mr. Garrison to teach chemistry because there was no carbon and oxygen to make Mr. Garrison. So, all right, that's what the universe made. So that doesn't answer the question, where did the carbon and the oxygen come from? Where did the gold come from that I'm made of? So what we have to do now is we have to follow this matter through the history of the universe. Where did the carbon come from? Where did the oxygen come from? Where did the gold come from? And the answer is let's follow this matter that the Big Bang makes. So the Big Bang, the universe is filled with all this hydrogen and helium gas. It's very rapidly expanding. The very first picture we have of the universe, the baby picture of the universe, is what I'm showing you right now. This is the glow left over from the Big Bang. It's called the cosmic microwave background, or the CMB. And this is an image of what the universe looked like 380,000 years after the Big Bang. We can actually use radio telescopes in space, satellites, to measure the radio waves that we get from the Big Bang. And this is the glow that's left over from the Big Bang. We know that glow was released when the universe was 380,000 years old. And what you'll notice about that glow is it's already clumpy. That gravity is already starting to pull things together. Because all this expanding universe, there's dark matter in the universe, there's regular matter in the universe, and gravity starts pulling it all together, and we start seeing lots and lots of clumps of matter. And that continues to this day. The universe starts very, very smooth, like you see there in the upper left panel. And as time goes on, the universe gets more and more clumpy because gravity is pulling everything together. And today, gravity has pulled everything into clumps that we call galaxies, which are the basic building blocks of the universe. And then inside galaxies, we have stars, which are the fundamental building blocks of galaxies. This is a picture of the Hubble Extreme Deep Field, which is one of the deepest images that humans have ever taken of the universe. And what you can see in this image is that the universe is quite clumpy, right? The gas is not spread out evenly, but it's clumped into these giant galaxies right here. Something else I want to mention about this image, because it's just one of the most amazing images that humans have ever taken, is that basically everything you're seeing in this picture is a galaxy and not stars. There are, in fact, in this picture, only a few stars from our own Milky Way galaxy, and they typically have a cross shape to them. So that's a star in our Milky Way galaxy. That's a star in our Milky Way galaxy. You can find a couple more in there. But altogether, there's like 5 or 6 stars in our Milky Way galaxy in here. Everything else you see in here are actually galaxies made of hundreds of billions of stars, but they're seen from so far away that they look like little blobs of light. So that's a galaxy like our Milky Way. That's a galaxy like our Milky Way. But the really cool thing to me is, see that little tiny dot right there? That little tiny dot? That's a galaxy like our Milky Way. 100 billion stars seen from so far away that even with the most powerful telescopes we have in space, it looks like a little tiny dot. And when you think of all the galaxies that are in this little tiny field, which is much smaller than the moon in the sky, that the whole sky must look like this, you realize that in addition to our Milky Way galaxy, there are hundreds of billions of other galaxies out there, each of them having hundreds of billions of stars in it. But we're not here to talk about the vastness of the universe, so I'll probably just leave it at that. This is what our Milky Way looks like if we could get outside it. It's not a picture of our Milky Way because we've never been outside the Milky Way. With the spacecraft that we have today, it would take us billions of years to get far enough away from the galaxy to photograph it like this. And of course, we haven't had billions of years to do that. We've only had space technology for less than 100 years. But this is another nearby galaxy. You can see its catalog number up there, NGC 4414. It's very much like what our Milky Way would look like if we could get outside the Milky Way. And our Milky Way galaxy, as most galaxies, primarily made of stars, right? So the stars are contained in 2 areas. There's the bulge of the galaxy here at the center, which is literally just like a giant bulge of stars. And then there is a disk of material that is spinning. And that disk is like a pizza. It's round, it's flat, and it's thin. So the disk of the Milky Way galaxy is round and flat and very thin. And we live about halfway out in the disk of the Milky Way galaxy there. And what you can't really tell from this photograph is there are just so many stars in the galaxy that all their light blends together. If you look at this carefully, you can see some individual stars in the galaxy, but the vast majority of stars just blend together. And what we want to do is we want to follow the life history of those stars, because it turns out the origin of the elements has something to do with stars and the way that stars power themselves. And so let's talk a little bit here for a minute about how stars power themselves. Our sun is a little bit bigger than your average star. So our sun is a bigger than average star. And the way our sun powers itself is, well, first of all, let's talk about what the sun is made of. The sun is a giant ball of gas. It's about, I mentioned earlier, 74% hydrogen, 25% helium, about 1% everything else. So for our purposes, we can say it's just a big ball of hydrogen gas. The weight of all these layers squeeze down on the center of the sun, and the center of our sun is very, very hot and very dense. It's very hot because the weight of all the overlying layers push on it and they increase the pressure. And you'll remember from the gas laws that if you increase the pressure, you also increase the temperature. So the temperature of our sun is about 15 million degrees down there, 15 million Kelvin, by the way. So it's about 15 million Kelvin down at the center of our sun. And it is so hot down there that when a proton and a proton collide with one another, every now and then they can combine to make that heavy form of hydrogen, and they can fuse eventually hydrogen into helium. That is, the center of our sun is so hot that it's undergoing nuclear reactions right now. Two hydrogen atoms come together to make a heavy form of hydrogen called deuterium. Another hydrogen atom combines with that to make a light form of helium. Two of those light heliums combine to make regular helium. The net result is that 4 hydrogen atoms go in and 1 helium atom comes out. Those nuclear reactions are what sustain the light from our sun. The energy released by those reactions is where the energy of our sun comes from. Every single second inside the sun, every single second inside the sun, 600 million tons of hydrogen are being fused into helium every second. Something that you probably learned in chemistry class is that mass is conserved in chemical reactions, right? If we have a certain number of reactants going in, the products have to have the same mass. That's no longer true when we talk about nuclear fusion. With nuclear fusion, it's the combination of mass and energy. It turns out this helium atom weighs a little bit less than the 4 hydrogens that went in. And the reason it weighs less is because that missing matter was converted into energy through E equals mc squared. And every second, our sun is losing about 4 million tons of matter. Every second, 4 million tons of matter is being converted to energy inside the sun to power the sun. So what that means is our sun is converting hydrogen gas into helium gas. And over time, eventually, our sun will run out of hydrogen. This is what the sun looks like today. That's what it looked like billions of years ago. That's what it's going to look like about 5 billion years in the future. You can see deep down in the core of the sun where the nuclear reactions are going on, it's converting hydrogen to helium. And eventually the core will run out of helium and our sun will become a red giant star at the end of its life. We'll talk about that in a minute. At the end of its life, our sun will actually get hot enough that it can fuse helium into beryllium and beryllium and helium into carbon. And our sun, as a red giant star at the very end of its life, can actually build all the way up to oxygen on the periodic table of elements. It'll fuse hydrogen to helium, helium to carbon, carbon to oxygen. But it will not make the gold in our periodic table, will not make the iron that's in our blood. And it turns out that carbon and oxygen, excuse me, is locked up in the dead core of the star. It never releases that carbon and oxygen into the universe. So this is not where your carbon and oxygen came from, because our sun won't do this for 5 billion years. And other stars like our sun, when they built those elements, it's still locked up inside the dead core of the star. In order to understand where the elements come from, we have to look at really massive stars. Because what really massive stars do, they're so hot that they can fuse helium to carbon, carbon to oxygen, oxygen to silicon, silicon to iron on the periodic table of elements. Really massive stars can actually build all the way up to iron on the periodic table of elements. And they stop at iron because of all the elements on the periodic table. It's the most stable of all the elements. It's the one that's most tightly bound together. So once you reach iron on the periodic table, you can no longer undergo nuclear reactions, fusion reactions to release energy. But anyhow, these massive stars build up to iron on the periodic table of elements. But how do those elements get back out into space? At the very end of its life, a massive star, which has puffed itself into a red giant, has a very tiny, dense core that's made of a big ball of iron down at the center. And around it is a shell of silicon that's fusing into iron. And around that is a shell of oxygen that's fusing into silicon, and a shell of neon that's fusing into oxygen, and carbon fusing into neon. There are all these shells inside the center of this massive star down there. And that big ball of iron can't undergo any fusion. And gravity starts to shrink it. And as it gets smaller and smaller and smaller, and it gets denser and denser, eventually gravity is so strong that the iron can't resist the pull of gravity, and in 2 seconds, it collapses. And when it collapses, it detonates the star in a massive explosion called a supernova. This is a picture of the Magellanic Clouds. It's a nearby galaxy that was taken in January of 1987. And in here is a star about to go supernova. And you can try and guess which star is about to go supernova. This is a giant star-forming region right here with some very massive stars in there. But if you were really good, and you'd be better than astronomers, because we didn't guess it, it's that star right there. That star exploded at the end of January 1987. It's called supernova 1987A. It was the first time in 400 years that we saw a bright star explode that was bright enough to be visible with the naked eye. So that's a massive star that looked like this in its last few days. And at the very end, the collapse of its core caused that star to explode. And as it exploded, it flung all of those elements, that carbon, that oxygen, that iron, out into space. But more importantly, and here's a picture of what's left over after this. This is the Crab Nebula. It's called a supernova remnant. It's an example of what happens when massive stars blow themselves up. We know that this particular one became visible in our night sky on July the 4th in the year 1054. And that's because Chinese astronomers kept such good records. We know the exact day that it became visible. But we're seeing this now 1,000 years after it blew up, and that's what that massive star looks like. And what you can see is, if you could measure this gas, it's all racing out at about 6,000 miles per second from the center. All that gas, that carbon, that nitrogen, that oxygen, that iron that was made in this explosion is being spread back out into space. Most importantly, is in the few seconds that the core of this star collapses, it gets hot enough and dense enough that the universe makes all the other elements on the periodic table. So to summarize real quick, this is what the Big Bang did: hydrogen, helium, a little bit of lithium. This is what stars like our sun do. They can make all the way up to oxygen, but they're not really good about sharing that carbon and oxygen. They keep it tied up in the core of the star. Massive stars make all the way up to iron on the periodic table of elements during their life. And then when they explode, they make everything else. Gold is precious to us because it is rare. And gold is rare because the star only had 2 seconds to make it when that star blew up at the end of its life. It didn't have millions or billions of years to make it. It only had a tiny amount of time to make that gold. So just to emphasize in the minute that we have left about did your atoms come from? Here is your history. Here is where your atoms have been. They were in the Big Bang. And they found themselves probably a few 100 million years after the Big Bang in a giant massive star. And that massive star fused hydrogen to helium in its core. But the first time you were in a star, your atoms probably weren't in the core. They were out here in the outer layers. And so your atoms were inside that star. At the end of its life, that star blew up and it returned your atoms back to the universe, but they were still hydrogen and helium. Your atoms were probably in a star-forming region a second time, and you found yourself in a second massive star that blew itself up and your atoms were returned out into space. Maybe the third time you were in a star-forming region, your atoms found themselves deep down inside the core of the star. And now your hydrogen was converted to helium, your helium to oxygen, your carbon to oxygen. Some of that, when that massive star exploded, was converted to gold. And this time, when all those elements were spread out into space in that titanic explosion, the next time they found themselves in a star-forming region, they weren't actually in a star, but they were in that dusty disk of material that surrounds newborn stars. When we look with the Hubble Space Telescope at newborn stars, we see they're surrounded by a ring of dust. That dust is forming planets. That's where your atoms found themselves the last time. And as that dust clumped together, eventually it formed our planet Earth. So that's where your atoms came from. You've been inside a star multiple times in the history of the universe, at least 3, probably 4 or more times in the history of the universe. And the last thought I'll leave you with is, think about what's going to happen to your atoms. You're made of oxygen. When you die, your oxygen atoms will be recycled on the surface of the earth through plants, through animals, through other people probably in the future. Eventually, when our sun becomes a red giant, it's going to vaporize the outer layers of the earth. And then as it vaporizes the outer layers of the earth, your oxygen atoms will be spread back out into space. This is an example of what happens when stars like our sun die. That's the dead core of the star, and that's the remains of the star. And that greenish color that you see actually comes from glowing oxygen atoms. That is your future. you will be billions of years from now inside a planetary nebula going back out into space so your atoms can be used again. All right, I'm going to end there because we're out of time. So I don't know if we have time for questions, Mr. Garrison.
We have tons of time for other sites. We'll be leaving, and thank you guys for attending. If you have to leave, perfectly fine. If you want to stay online and ask questions, just yell out your questions. We are here until about 10:20. So by all means, if you have questions at other sites, ask them. We can start with any questions that we have here in Riverbend as well.
Yes.
Do we know at what rate the universe expands? Has that changed since the Big Bang?
So do we know at what rate the universe is expanding? Yes, absolutely. That's a parameter that astronomers absolutely need to know about the universe, is how fast it's been expanding, and it absolutely has changed in the history of the universe. So the universe initially is expanding very quickly, but gravity is trying to pull all that together, and so the universe is slowing down over time. But what we recently discovered about 20 years ago is that slowdown is stopping, and the universe is actually starting to accelerate again. It's starting to go faster and faster. So there must be something that's causing the universe to accelerate faster and faster. We've given it a name. We call it dark energy. It's I'm not particularly fond of the name, but the word dark actually means we just don't know anything about it. And we know it has to be a form. Well, it's not a form of energy as you and I usually think about it. It has something to do with the fabric of space and time itself. But this dark energy is causing the universe to expand, to accelerate, to go faster and faster over time. Again, whoever discovers what dark energy is absolutely going to win the Nobel Prize in physics. So, yes.
We have a question at Colonial Forge. And
Yeah, go ahead.
Could you talk a little bit about the role of entropy in this whole process of the expanding universe?
Yeah, so entropy, the universe as a whole is a much harder one to talk about, because usually when we talk about entropy, we're talking about sort of closed systems where we can measure things. But well, let me ask this question. What specifically about entropy did you want to know?
So we watched a video yesterday in class that talked about the role of entropy in actually the origins of life, in that life itself is contributing to entropy overall in the universe. And some of the theories on the origins of life have to do with the impact or the role of entropy.
Yeah, so yeah.
Can you give them a quick definition of entropy? Some of the classes have not yet started heat.
Yeah, okay, so a quick definition of entropy. Oh man, now I'm on the spot. So
Yes.
because I don't usually teach about entropy,
No,
but
that's okay.
But the simplest term that I like to think of entropy is sort of the randomization or of chaos, yes,
Yeah.
of the universe. Basically, if you think of stacking your textbooks, take a bunch of textbooks and you stack them really high, and they're nice and neat and orderly, and then you spread them all out and you just sort of scatter them around. When you scatter them around, you're increasing the entropy of them. And the laws of thermodynamics say that entropy in the universe, or entropy in a closed system, is always increasing as you undergo, well, it's always increasing. And so then people look at life and say, but wait a second, life is very, very organized. So if life is very organized, doesn't that violate the laws of thermodynamics? Because thermodynamics says entropy is increasing, but to create something like me, which is very highly organized, it's reducing entropy. And the answer is the laws of thermodynamics say that it's perfectly fine to reduce entropy. You just have to add energy to it. Think about those textbooks that are spread out all over the case. I can reduce entropy by stacking them neatly, but I have to put a lot of energy into doing that. And so as long as you're expending energy, you can absolutely reduce entropy. And that's the question about the origin of life. That I don't see any problem with is life, right? The whole point of life is taking energy from your environment, whether it's photosynthetic or chemosynthetic, or in our case, we're growing vegetables and eating animals. Life is bringing in energy, and it's using that energy to organize itself. And so I don't see any violation of the laws of thermodynamics there. I don't know if that helps or what you were looking for.
Very good. Thank you.
Yes.
We have a question over here at Fosse side.
Yeah, go ahead.
Why do galaxies spin in a spiral?
Why do galaxies spin in a spiral? So they spin because they probably started off with just a tiny little bit of random motion. And as they collapse, that random motion turns into spin. And the best way to analogize this or to think about it is think about an ice skater. An ice skater, when she's spinning with her arms out, is spinning really slow. And if she pulls her arms in, she spins faster and faster and faster. These galaxies, I'm going to flip way back to a picture of a galaxy here. These galaxies, when they're forming, they're just through random motions, clouds moving this way or that way. They probably have a little bit of random motion, but as the galaxy collapses, it spins faster and faster and faster. And eventually it's spinning so fast that the centrifugal force is balancing the force of gravity. And where the centrifugal force balances the force of gravity, the material doesn't fall down to the center, but it stays in that thin, flat disk. So if you think about all the stars that are orbiting the galaxy in that disk, they're orbiting because gravity is pulling them towards the center, but their centrifugal force, their orbital motion, is keeping them supported. And it forms a disk because if you think about what happens at the poles it pulls in, but the spin can't support it. It can only support it around the equator.
Yeah, a magnet. This is one only to.
Will you give the PSA for your observatory night at
Yeah.
UVA? Do that.
These-
So if you're visiting Charlottesville and you're interested in astronomy or the physical sciences like physics, you're welcome to come visit me. I'm always happy to meet with students and talk to you about what it's like to come to school at the University of Virginia. If you happen to be there on a first or third Friday night, we have an observatory that's open to the public on the first and third Fridays of every month. So,
Okay, now.
question.
So what do you know about what happens when galaxies collide? Is it our galaxy, like?
Dr.
Yes.
Yes, that's right. So our Milky Way galaxy, the nearest big galaxy to us is the Andromeda galaxy. And we're actually close enough together that the force of gravity is able to overcome the expansion of the universe. And it's actually pulling us together. And between 3 to 5 billion years from now, our two galaxies are going to collide. What's really interesting about that is it's just driven by gravity, Newton's law of gravity. And so as these two galaxies come together, as they collide with one another, keep in mind that this galaxy is not a solid. It's made up of hundreds of billions of stars. And those stars are little tiny things with lots of space in between them. And the other galaxy is made of little tiny stars. And it's funny to think of stars being tiny when you and me, they're huge. But on the scale of a galaxy, they're tiny. The other galaxy is made of tiny stars with lots of space between them. So as those galaxies collide, the first thing that happens is they just pass right through one another. But now the gravity is so strong that it pulls them together and that they end up merging in a really messy merger. But when we look at with the Hubble Space Telescope and look at merging galaxies, we see thousands and thousands of galaxies that are in the process of merging. Everything from the beginning stages up to galaxies that are probably well merged. In fact, when you look in the Hubble deep field like this, you'll notice that there are these particularly reddish colored galaxies right here that don't look like spirals. One of our really well-supported hypotheses today is that these elliptical galaxies actually form from the mergers of spirals. So, and what happens is as they merge together, the clouds of gas, which is not like the stars just go past one another, the clouds of gas actually hit one another, and that triggers star formation, and you end up with this huge burst of star formation. But then the galaxy uses up all its gas, makes all its stars. And now what you're seeing are galaxies that have run out of gas to make new stars, which are young and hot and blue. And all you see are the old red stars in those galaxies. So,
We have
Other
another
questions?
question.
yes.
Why do most galaxies have a supermassive black hole at the center of them?
Boy, if I could answer that, I would be famous in the world of astronomy. We don't know the answer to that question right now. That is a very active topic of research in astronomy. For those that don't know, the question was, why do most galaxies have a supermassive black hole at the center? Essentially, every galaxy that we look at, including our own, has a supermassive black hole down at the center of the galaxy. In the case of our galaxy, it's a couple million times the mass of our sun. In the case of some of these elliptical galaxies, it can be 1 billion times the mass of our sun. The biggest ones are a few billion times the mass of our sun. What we know from them is that they formed as the galaxy formed. So with telescopes like Hubble and now with the James Webb Space Telescope, the early question in astronomy was, did the black holes form first and the galaxies formed around them? Or did the galaxies form first and then the black holes formed? It turns out it seems to be symbiotic now. The black holes and the galaxies are forming together at the same time. But what's causing the black hole to form, we just don't know the answer to that right now. But that is a very active topic of research. Yes.
And now- We have another question at Forge when you have a second.
All right, let me answer this question here first, and then I'll do the distant one. So the question was, what are the odds that there's another planet out there like the Earth, right? And that's a whole separate lecture I can give, but I'll give the quick answer to that. Let me find my picture of the Earth right there. Is that astronomers have discovered over the last 25 years that planets are very, very common. Essentially, every star has planets going around it. Right now, we have mapped out more than 5,000 other planets going around other stars out there. So we know planets are common. We know that Earth-sized planets are common. They're not the most common kind of planet, but they're not rare. We've also discovered that Earth-sized planets that are the right distance from their parent star to have liquid water on the surface are also common. That means it's not rare to find a planet the size of the Earth that it's at its right distance from its parent star to have liquid water on the surface. And what I mean by the right distance, it's not too close and too hot, and it's not too far and too cold. But I'm afraid that's where I have to leave the story, because that's the best that my generation's been able to do. We cannot look at an Earth-sized planet and determine whether it has liquid water or not. Your generation is going to have to build the giant telescopes, and I mean giant telescopes. They're going to be necessary to look at these Earth-sized planets and determine whether they really have liquid water on them or not. That's a telescope that's probably 20 or 30 years away in the future. So that's something your generation's going to do. After that, once we know they have liquid water, then we could search for signs of life in the atmosphere of those planets, but that's even further away. So I think Earth-sized planets, well, I know, because we have data to prove it, that Earth-sized planets are common, even Earth-sized planets in the habitable zone. But whether they're Earth-like with water or not, we just don't know. Let me take the remote one. So there was a remote question.
Question is, could you comment on the James Webb Telescope, what it's looking for, and some of the controversy around the fact that it's finding galaxies that seem to be too big to exist where they currently exist?
Yeah, no, terrific. So the James Webb Space Telescope, what it is doing is taking pictures. James Webb is like the Hubble Space Telescope. It is a Swiss Army knife of telescopes. It does everything, right? There's instruments on board to take pictures. There's spectrographs on board. So it's contributing to lots and lots of areas of astronomy. So it's teaching us how stars are born. It's teaching us how planets form around stars. But one of the more interesting results that has come out of James Webb is that when we take really deep pictures of the universe like this, and by the way, this is a Hubble image that I'm showing right now. It is not a James Webb image. James Webb has yet to take and release its first deep field like this. But the early images from James Webb are showing that some of these really tiny galaxies, and by the way, the whole point for James Webb, or one of the main points, is when we look at these little tiny dots in this photograph that are galaxies like our Milky Way that are so far away, they look like little dots. James Webb can actually show us what they look like and what they're made of. We're seeing some of them are just bigger than we expected. We don't have the answer to that yet. Astronomers are very actively working on that as well to try and figure out how those galaxies got so big so quickly. So we don't know the answer to that question because it literally just came out of James Webb. So I wish I could tell you exactly why and how they got that big that fast. We just don't know.
Yeah, that's another Nobel thing.
Yep, exactly. Yes. Right. So the question for those online that couldn't hear it is, if we were to travel a long distance at a very high rate of speed and come back, why would we not age as much? And that comes from Einstein's special theory of relativity. And Einstein's special theory of relativity says that when you're moving very quickly relative to someone else, time flows slower for you than it does for them. And it just falls out of special relativity. And what's fascinating about special relativity is there are lots of weird things that happen. Length gets contracted, time slows down, mass increases. And you would think that all of these things, they're just so non-commonsensical that they can't possibly be true. And yet we've tested special relativity over and over and over again. And we see that it absolutely holds. Every test we've ever thrown at relativity, it has passed every test with flying colors. And it turns out you and I use it every day, right? When you take your cell phone outside and it tells you exactly where you're located on Google Maps, you're using the GPS constellation of satellites. And those satellites have to correct for relativity because they're moving relative to us. And the way we measure where that satellite is so that we can figure out where you and I are is they have very accurate atomic clocks on board. But compared to you and me, those clocks are running slower than an atomic clock on the Earth because they're moving relative to us. And so we have to fix that. And if we didn't fix for that, GPS wouldn't work. So you're actually using relativity every day and don't realize it. But you can get in, I'm not going to try and explain the physics behind it because it actually requires a lot of algebra. Nothing more than algebra, but just algebra. You can see why time slows down when you're traveling very quickly. So, yes.
Do we know how or why like energy colliding makes it matter?
Yeah, do we know why when energy collides that it makes matter or antimatter? Yes, absolutely we do. So there is this idea that physicists have built up over the last 50 years that explains how matter is put together, explains all the particles that we have, and it explains how those particles interact with light, and it's called the Standard Model. And the Standard Model does an extraordinarily good job of predicting what the matter in the universe is like and how that matter interacts with light. And so inside the Standard Model, we know that if you have two photons of light colliding, that energy can go into making the matter that we see. So, yeah. Yes.
This might be a dumb question.
No.
But the physicists assume that when the universe is expanding, do they assume it's pushing against something, or do they assume it's just going into like free space?
So, yeah, so it's a great question. The question is, as the universe is expanding into empty space, or is it pushing against something? And I'm going to correct your assumption, which is that the universe is expanding into emptiness, or that it's expanding into something. So it's kind of hard to wrap your head around. But when I teach about the Big Bang, I'm very, very careful to say that the Big Bang was not an explosion. It was a rapid expansion of space. So when you and I think of an explosion, right, we think of like an empty room and something explodes in the room and all that stuff is coming out and it's filling the empty space of the room. The thing to know about the Big Bang is it not only made the matter that's in the universe, but it actually made the space and time in the universe itself. So that is the universe in the expansion, this rapid expansion, actually made space. It's not that space existed and was empty and the Big Bang happened and we're just trying to fill all that space. It turns out space itself was made as part of the Big Bang. One thing we don't know is whether that space is infinite and goes on forever, or whether it's finite and has an edge to it. All we know is that we can see to the visible edge of the universe, and we know that the universe must be a couple times bigger than the universe that we see. But other than knowing that it's a couple times bigger than the universe that we see, we have no idea whether it ends out there, whether it continues forever, or really interesting, whether it wraps back on itself. We just don't know. So, are there any online questions? All right, yes.
So where do like electrons and neutrons come from?
So electrons and neutrons come from the same place that protons and electrons, protons came from. So when you have two photons of light, electrons are much, much less massive than protons. So they're actually a lot easier to make than protons are because they require a little bit less energy because they're just lighter. So let's work this then. So neutrons and protons, which is heavier, a neutron or a proton? Neutrons. Neutrons are actually slightly heavier than protons are. And so neutrons are a little bit harder to make than protons. And I'll work this out. Not everybody might get this, but do you mind if I write on the board, Mr.?
Please help out.
There's-
They
So-
had a chance to write there.
All right. So the universe, because protons are less massive than neutrons, it's easier for the universe to make them, right? And so when the universe makes protons and neutrons, it makes one neutron for every 6 protons. So that's a proton, 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 proton. Okay, and that's one neutron. Yeah. And it just made less neutrons because they're harder to make. It also turns out they're unstable. Neutrons, a free neutron is unstable in a decay. So let's do that again. We make another neutron and we make 6 protons.